All right, IB AA SL2. Today we're going to do a few more specific examples with the binomial distributions and learn one new formula. I guess one and a half new formulas. One of them's not that new. So first question we're going to do is a box contains a large number of carnations, a quarter of which are red. The rest are white. So we don't know how many carnations are in there. Carnations are picked randomly from the box. How many carnations must be picked so the probability of at least one red carnation is greater than 0.95? Well, first, this is a binomial distribution. So the notation that just represents the whole binomial distribution is B, and then we don't know how many flowers there are. So I'm going to represent that with N. But I know the probability of getting a red carnation is 0.25. That's 1 out of 4. So they're asking us how many carnations we must pull out so the probability of at least one red carnation is greater than 0.95. To put that into notation, that means the probability of getting X greater than or equal to 1, so probability of at least 1, is bigger, it's a terrible alligator, bigger than 0.95. So we need to solve this. The first thing that really triggers me here is the probability of at least 1. We've seen this come up multiple times where the probability of at least 1 is 1 minus the probability of none. So I'm replacing that left-hand side with 1 minus the probability of none. Now, the probability of none, in this case, if I use the binomial distribution formula, is n choose 0, 0.25 to the n, to the 0, because we're getting no red flowers, and then it would be 0.75 to the n power, and then this is greater than 0.95. Now, we're going to start to clean this up. First of all, anything choose 0 is just 1. I guess maybe you guys, if you think about it in relation to Pascal's triangle, that makes sense because it's like the very first term is always a 1 on those rows. So that's a 1. Also, 0.25 to the 0 is also a 1. So I can clean this up just a little bit and say this is the same as 1 minus 0.75 to the power of n is greater than 0.95. Now, we need to solve this, and it's been a while for you guys. We're going to try to get the n by itself. I guess there's two ways I could go about this, but yeah, I'll keep it on the... I'll remind you guys of some properties. Okay, first I'm going to subtract 1. So we get negative 0.75 to the n is greater than... When you subtract 1, you get negative 0.05. Then I don't like this negative on the outside, so I'm going to divide both sides by a negative. But anytime you divide by a negative, you have to flip your alligator. So we need to figure out what value of n makes this whole thing true. To keep getting n by itself and try to go for like a pretty exact answer here, we're going to take the log of both sides. Anytime you have a variable in a power spot and you need to get it out of the power spot, you can log both sides. Then there's a property of logs where this n gets to come out in front and be a big N. So this is n log 0.75 is less than log 0.05. Then divide both sides by log 0.75. So n is less than log 0.05 all over log 0.75. Then if you crunch this on your calculator using that log button, you get n is less than 10.4. So, hold on, I feel like I got my sign backwards somewhere. We kept it greater than in the beginning. And then at this stage, the alligator was towards the 0.05. Log 0.05. Why did that switch right there? I think the book might have made a mistake with that. The n is less than 10.4. When they divided both sides by log 0.75, they switched the sign. Sorry, I wasn't ready for this. At any rate, you can't really have 10.4, so they want to know when it gets above 0.95. So it would be the term right after 10.4. So at least 11 carnations must be pulled. Main point of this problem, that you guys kind of remember how to do logs, how you use logs in solving to get those power spots out of there. All right. Now, for a binomial distribution where it's just a binomial, just I shouldn't use the word normal, it's a very regular binomial distribution. The expectation of x is e of x equals n times p. So this is like the expected value of the distribution. This is very easy. You just take the number of trials and multiply it times p. So a quick example of that, a biased dice is thrown 30 times and the number of sixes seen is 8. So the probability of a 6 is 8 out of 30, which is 4 out of 15. If the dice is thrown a further 6 times, find the expected number of sixes. Well, first of all, this distribution, if we want to throw it into that wacky notation, is xb. We're throwing it a further 12 times, and the probability of a 6 is 4/15. So then the expected value of this is just going to be these two things multiplied together. So it's n times p, which is 12 times 4/15. And then 12 times 4/15 is 3.2. So that's the number of sixes you would expect within 12 throws. You wouldn't want to round that to 3 because you're like, oh, you can't have a decimal, number of sixes. But with the expected value, it's like an average, so just keep it as a decimal. The formula for variance of a binomial distribution. So we're starting with a regular distribution again. And the formula for variance, first of all, is the notation is little sigma squared. And it's just n times p times q, where q is the, here, I'll write that in. The q is the same thing as, it's the complement of p. So it's 1 minus p. So an alternate version of that is just np times 1 minus p. This next example, a biased dice is thrown 50 times and the number of sixes seen is 12. So the probability of getting a 6 is 12 out of 50. If the dice is thrown 12 more times, find the probability that a 6 will occur exactly twice. Well, we're dealing with another binomial distribution where we're throwing it 12 times and the probability of getting a 6 is 12 out of 50, which is 6 out of 25. So the probability that it goes exactly twice is 12 choose 2, 6/25 to the, well, we need 2 of them. And then the opposite of that would be what, 19/25? The complement, and that's going to be to the power of 10. Notice that these two numbers, 2 and 10, always add up to the n that you're going for. So if you use your calculator for that, this turns out to be 0.244. Find the expected number of sixes. So the expected number of sixes is just going to be how many trials times the probability of getting a 6. So 12 times 6/25 is 2.88. That's how many sixes you would expect in the next 12 throws. Last part, find the variance of the 6's. So the var of x, a reminder, is n times p times 1 minus p. So this would be 12 times 6 25ths times 19 25ths, which is 2.19 to 3 significant figures. Remember that variance just kind of tells you the spread of the 6's, like how far out, like how far they're distributed from the mean sort of thing. Yeah. They don't go into too much interpretation about what that number means. They just like want you to be able to find it. So it's pretty easy if you got that formula, which I think might be in your formula booklet. Although we were realizing recently your formula booklet doesn't have the binomial theorem in it, which is wild because they give you like the area of a rectangle and you're like, cool, I know length times width. Could you give me the binomial theorem? But they don't, so we need to know it. All right, you guys, happy studying. Ask me questions.